Welcome back. We're going to continue with what we left off yesterday with Huffman Coding. This is Computer Science 3, CSCE 310. Reminder, as always, we're on Piazza with a live Q&A, so if you've got any questions or if you notice any technical issues or difficulties, please let me know about that so I can try to fix them. So we were talking yesterday a little bit about coding theory. We don't need a huge background in it in order to do this exercise or understand what Huffman coding is. But basically, there are two branches of coding theory. That you can add redundancy to a signal in order to account for packet loss, right, over a network or something like that. Or you can add redundancy to ensure against data loss, like CDs, for example. Use additional encoding so that when you scratch them, it can be recovered. Error correction, error detection. What we're going to be looking at is the opposite of that, compression, where you are trying to either take information out, redundant information out, or encode it into a smaller bit of information, right? And Huffman coding is a lossless encoding scheme in that it's not going to lose any of the information. Some encoding schemes are compression algorithms are lossy, like JPEGs, MP3s, MP4s. They either cut out data or they approximate data in order to result in smaller file sizes. We're going to try to have a lossless encoding scheme. Before we do that, let's do some. Let's get some definitions out of the way first. Let sigma right here, math mode, be an alphabet of size n. Right? For our purposes, our alphabet is simply just going to be a binary, right? So sigma equals, and we may revisit this notation later on. That star up there is from a regular expression. So hopefully you might be familiar with regular expressions like find and replace, or find everything that looks like a telephone number in a large file, something like that. And star means 0 or more occurrences of. And so when I apply it to this this set over here, this 0-1 set, I'm looking at all binary strings. So don't worry about the details of that, the mathematics of that. This is just the set of all binary strings. Right? We'll come back to that later on when we look at computability theory, because that's how you look at problems from a theoretical point of view. You look at them as languages. You look at them as sets, infinite sets of subsets of all binary strings. Okay. A coding or encoding is a mapping of your alphabet to sigma. Right. There we go. Right. Of a not your alphabet, a character set to sigma. Right. So basically, what that means is that for example, a block encoding or fixed length encoding scheme maps your characters to a fixed length code word, or two fixed length code words. Right? For example, ASCII. We'll just look at the extended ASCII character set. Capital A has a value of 65. That in binary, that's going to be 0, 1, bunch of zeros, and then 1 at the end, right? So it maps it to these 4 bits over here, right? And again, like A, I'll backtake this. A maps to, again, hopefully I'm right off the top of my head here, 0, 1, 1, 2, 3, 4, 5, 6. No, too many zeros. There we go. Right? Is that how many zeros? One more. There we go. Not too many zeros. There we go. I believe that's 65 in decimal. Right? Correct me if I'm wrong on that. I'm just doing that off the top of my head. Go ahead and post in Piazza. Let me know if anybody's alive out there, right? And with confirmation that that was correct. All right. But that kind of encoding scheme, as we briefly alluded to yesterday, is not ideal because A, E, I, O, U. Certain letters in the English language are far more common than other letters. For example, X, Y, Z, or Z, for example. You might have a text file that doesn't even have Z. The space is going to be far more common than any letter because it goes between every single letter or every single word. Capitals may be less common than lower cases in a typical text file. So by encoding it with a block encoding scheme, a block encoding scheme requires log base 2 of n, where n is your alphabet size, your character set size, bits per character, regardless of their frequency. Okay? Alternatively, we could create what's called a variable length encoding scheme, where more common letters, or characters, I should say, are given shorter code words, and less common are given longer code words. Right? So the point of doing that is that you reduce the average code word length. The payoff is that your average code word length is reduced. Right? Instead of doing just log n bits everywhere, for example, if you had 8 characters that you had to encode, and you did a block length encoding scheme, a fixed length encoding scheme, then everything needs 3 bits. Whereas, suppose that one of those letters that represented 99% of your entire file, you could represent that with 1 bit, and then all the other characters, you could represent that with, say, 4 bits, right? So some of the characters are going to end up being longer code words, but the payoff is that 99% of them can be encoded with only one single bit. In fact, if it's that skewed, then there are better ways of doing it. Just to record. Okay, great, I got it. Thanks. That's the payoff. The average code word length could be lower, and we'll see an example of this later on, right? You end up with compression for English from 25 to 40% smaller files. Right? So there is a big payoff here that when you store stuff or when you send it through a network, if you can send 25% less information that use 25% less bandwidth, that means that your transmission is going to end up being 25% faster, right? Okay, but there is a problem here, right? Such encodings need to be prefix free. Right? So for that, I'm going to go over here and I'm going to propose the following encoding. Say that we've got A, B, and C, A, B, C, and D. In other words, just 4 characters that we want to encode. What if we wanted to do 0, 0, 1, 1, 0, 1, and 0, 1, 0, right? Now what we mean by prefix is this first code word, which is just a 0, is a prefix of this, and it's a prefix of this one, because 0 appears in front as part of the code word before, right? This is a prefix of this one over here, because 0, 1, that's how this code word begins, okay? So what if this was my transmission? What if at the other end you receive the following: 0, 1, 0, 0, 1, 0? How would you decode that if this represented A, B, C, and D? Right? Well, I could represent this as two D's, right? D, this one, D, D, right? What's another way that I could, decode this? Well, it could be that this was actually a B, two A's, and another, sorry, that won't work out. But we could say then another B and then an A, right? It's ambiguous. We don't know what was actually sent because it's not prefix free. How do I know where one code word begins and the next code word and ends, and then and give me the next code word here, right? What I need is a prefix free encoding. For example, what if we did 10, 010, 110, and 0110, right? Now this is a prefix-free code because this does not appear as the beginning of as the prefix of any other code word here. This one does not begin as the prefix of any other code word. And likewise, all pairs here are prefix-free. So now there's no ambiguity here at all. If I transmitted, well, if I transmit 10, 010, right? I don't have to process this twice. There may be a way to disambiguate this using dynamic programming, something that we'll take a look at later on. But what I want to do is I just want to read this once so that I can decode it immediately. I want this to be efficient. So if I start at 1, well, that means that if I'm just looking at this code word from 1, well, it could be this one or this one. The next one is a 0. Oh, okay. That disambiguates it. It's definitely an A. And I know that that code word is done. B, C, and D. And then I go on to the next bit. Okay, 0. Well, it could be B or D. 1 could still be B or D. 0. Oh, it has to be B because that's not a prefix anymore. So B. All right. Start reading more bits. 0, it could be B or D. 1, it could be B or D. And now it can't be B anymore because it's 010. So I know I can then just jump to the end of that code word and decode it as a D. Right? So we need a prefix-free code for all of this stuff to work. Okay. So my solution is going to build a tree. Right. So the solution: build a tree with code words. Build a tree with characters at the leaves, right? Because it's a tree, every path from the root to a leaf is unique, right? We'll associate 0 and 1 with left and right traversals, edges going down, left, right, right? And be consistent about it. If you go down left in this tree, then that represents a 0. Go down right in that tree, that represents a 1. And so once we do that, then the path from any vertex, from the root to any leaf, defines a code word. Right? And because the paths are unique, you could have a path. Here are 2 leaves down here. You could have a path here. Just draw it over here. There are 2 leaves down here, and here's the root up here. You could have a path going to these that is the same for some part, but then at some point that it's going to have to diverge. And that divergence right there, 0, 1, means that this will not be a prefix of this one when you rebuild this path going down. So we get a prefix-free code. Furthermore, what we'll do is we will associate common, right, more frequent characters with shallow leaves, right, and less frequent characters with deeper leaves. And what this does is it ensures that because the code word is defined by the path from the root down to the leaf, then if it's shallower in the tree, then that'll be a shorter code word. If it's deeper in this tree, then that means that it'll be a longer code word. And we kind of and so we're achieving our goal here of trying to minimize the average code word length. We're not going to get into the mathematics of it, but you can show that this is optimal. According to Shannon's entropy theorem, or Shannon's entropy definition, that it achieves the lower bound defined by Shannon. Okay. Instead, I'm just going to show you how it works, because you will be programming this as part of your second assignment here. Okay. There are already Huffman coding tools out there, of course, that you can use. A common Unix utility called pack is, I believe, straight Huffman coding. But there are other encoding compression schemes, Ziv, Limpel, or encoding that takes Huffman coding and then takes it a step beyond. Instead of just encoding a bunch of individual characters, it looks for sequences of commonalities. And if you can find sequences of commonalities, you can encode an entire word. One use case for that, for example, would be XML data, where tags are repeated over and over and over again. If I've got student data represented as XML, then I've got a beginning student tag, an ending student tag. The word student, that could be encoded with a 0, right? And then I get away with all those letters, which would be 1 byte each. I'm getting away with only 1 bit for all that entire word, right? But we're only going to take a look at the simple version of this Huffman coding. Okay. So here's the basic idea. Right. We will start by creating n single node trees, right? Each associated with, actually, I'll start by computing the frequencies of all the characters in a particular file, right? When we do Huffman coding, it's for a particular file and a particular probability distribution within that file. If you go and change a file and use Spanish instead, Spanish has potentially, I don't know, a different distribution on on the common letters, right? So one Huffman coding will not work for, it won't even work for every single English file. We could have an English file with a lot of Z's thrown in there for artistic reasons or whatever. I don't know. But each encoding is going to be unique to an actual probability distribution. Right? So we start by computing the frequencies of all the characters in the file. In particular, if the frequency of a letter is 0, like there's no Z's in the file, then we don't even have to encode that at all. We can leave that out of our encoding scheme. So that's the first step. Is computing all those frequencies. Assuming that we have those frequencies, that is, of course, of practical interest, because that's how you're going to have to program it. But from a theoretical point of view, we're just going to step right in and assume that we have those frequencies. Then we'll create n single node trees, each associated with one character and its frequency. And by frequency, we'll just simply mean that this character A appears 15% of the time. That is, if you chose a random character out of this file, then there's a 15% chance that it's going to be an A. This file consists of 15% A's, 25% B's, 60% C's, right? That's what we mean by frequency. And then we will start combining trees, subtrees, by combining the least weighted trees first. Right? When you combine a tree, you create a new root node and give it a weight that is the sum of its the weight of its two subtrees. And the weight, of course, of a single node tree that contains a character, the leaves, that's going to be, the weight of that tree is going to be the frequency of that letter, right? You stop when you have only one tree left, right? And that's your Huffman tree. That is what's going to define your code words. Okay. So for this, let me go ahead and pull out another piece of paper here, and let's look at an actual example, and then we'll develop the pseudocode to do this. I typically do this on a whiteboard so that I can erase it if I need to, but I'm going to do it with a pencil here because I'm going to want to, move some stuff around, right? and erase some stuff. I might end up just crossing it out. So suppose that we have the following code words. A, code words, A through G. And since I'm using pencil here, let me know if this is not viewable at all, and I can switch over to a pen. All right. But otherwise, each one of them has some frequency. So instead of drawing out the frequencies and then drawing the single node trees, what I'm going to do is I'm going to do it all in one step. So I'm going to associate the leaves with this this box representation. That's a node in a tree, right? A has frequency, say, 0.10. In other words, 10%. 10% of the characters in our file are A's. This is another single node tree here, B, and suppose that it has 15%. C, suppose that it has 34%. So 34% of all, this is the most, you're going to end up being the most common character. 34% of all letters in our file are going to be C's. D, that's very infrequent, right? It's only 5%, right? And of course, you can normalize these. These don't have to be on the scale 0 to 1. They could be on 0 to 100 if you want. It doesn't matter as long as you're consistent about it. So E's are 12%, F and G's are 0.21% or 21% and 3%. Respectively. So here's a very simple input. I mean, you can think of all the English sentences that you can come up with that only represent these letters, right? But of course, we'll give you real English files as test cases for your assignment. So the encodings will be actually rather large. This one is just an example in order to show you how it works. So again, what we're going to do is we're going to go through, and we've got a collection here of 7 trees. 1, 2, 3, 4, 5, 6, 7. These are trees. It's just that they're single node trees. We can call those seeds if you want. So there are 7 trees here, and we want to start combining them. How many combinations are we going to make? Well, once we combine 2 of them, that leads to only 6 trees. If we combine 2, and we put that resulting tree back into consideration. So that results in 6 trees. We then choose the 2 most common, the 2 least weighted trees out of that. We combine those, and that'll lead to 5 trees. 4, 3, 2, 1, and then finally that's when we stop. So we're going to do this operation n-1 times. And the first operation here is going to take the 2 least weighted trees, D and G, and combine them. D and G. I'll rewrite them over here. 0.03 and 0.05. And now these are out of consideration. These trees are gone. Because I've created a new tree with a new root node, and the weight of that tree is simply going to be the sum 0.05, 0.03, 0.08 of its 2 subtrees. Now I have 1, 2, 3, 4, 5 single node trees and this 6th tree over here. Okay, it's clear and ready. Let me go ahead and switch over to pen. All right. That's okay. I'll just cross these out over here. Okay. This is D 0.05 and 0.03. There we go. A little bit sharper there. Okay. All right, so there's my new tree, and I've got 1, 2, 3, 4, 5 single node trees and this entire tree over here, the 6th tree. It's still in consideration. So if you want to, you can throw. Imagine that you've thrown it back over here, and you've got all 6 of those trees that you're under consideration. You then take the next 2 that are least weighted. Well, it's still this is 0.05, and the other least weighted one is this one over here. Let's see, what I was doing over here is I was putting the least the least weighted on the right, and this one over here. It doesn't matter when you could put the larger one to the left and the smaller one to the right, or vice versa, or switch it up every single time if you want. When you go to program this, of course, you'll want to be consistent, just because you don't want to throw in a randomization line just for no reason. It doesn't matter. All of them will lead to equivalent codes. Right? It doesn't matter if you've got a bit string of length 4 and it's 0011. You could flip all the bits, 0s to 1s, 1s to 0, and you'll have another encoding. It's still going to be prefix free, and it's still all the same lengths for everything, etc. It's just going to be a different encoding scheme. Right? 0s become 1s, 1s become 0. It doesn't matter, as long as you give as long as it's prefix free, and as long as you give the same length encoding to every character that you have to combine. So I'll just go ahead and put it over here, because unfortunately I've drawn myself now into a corner. I'm not going to be able to erase this. Once I combine this, 0.18 is the sum. This subtree has a weight of 0.08. This one has a weight of 0.1. And so the total weight here is 0.18. And now this is out of consideration. So I'm left with 1, 2, 3, 4, 5 trees. Okay? The next 2 that are least weighted are, let's see, this was 0.15 and 0.12. So B and E over here. And I'll go ahead and put B on the right-hand side, E as on the left side as the left child, and E over here. B has 0.15 and E has 0.12. Right? B is gone, E is now gone. And they've been combined into a new root node of the sum of these 2, which is going to be 0.27. Okay? Now I'm left with only 2 single node trees and these 2 trees over here. So I still have 4 trees. Right? Now I combine the next 2. That's going to be 0.21 and 0.18, the least weighted trees. 0.21, and this was for F. There we go. That's now gone. I combine it with this one over here. And now that's the sum there is 0.39. Let's see. The next 2 that are least weighted are going to be, well, C and this one over here. So I'll go ahead and put C right here, and 0.34. Combine those into 0.61. And then the last step here is going to combine the 2 remaining trees into this one up here, 1.0. Okay? Now, you're going to associate with each one a code word. 0, 1, 0, 1. Always be consistent about it. 0, 1, 0, 1. This is where you do need to be consistent and go 0 to the left, 1 to the right. You can go 1 to the left and 0 to the right, again, as long as you are consistent about it. So now, you'll note here that every character that we want to encode is a leaf. The unique path starting from the root down to that character is going to form a code word, right? Depending on if we go left or right. So over here, let me go ahead and write it down so that we have another copy. Right. A will be associated with, well, where is it? Right here. 0, 0, 1. B will have a, where is it? Right there. 1, 0, 0. C will have an association of 1, 1. Again, the most common ones, and this is certainly the most common, are shallower in the tree. The least common ones, like D, is going to be deeper in the tree, and given 0000 as a very long code word, at least according to this input, with four of length 4, right? Likewise, G, E, F, and G. Let's see, E is over here, so 1, 0, 1. F is over here, 0, 1. Right? And G is over here, 0, 0, 0, 3 zeros and then a 1. Right? Now, if you want a hint on how you might be able to do this easily with in your program, I would keep references to all, once you create all the single node trees, I would keep references to all of them in a list somewhere. And then instead of, you could do a full, pre-order traversal, and then every time that you hit, and maintain where you came from, and every time you hit a leaf, output whatever string you've built up so far. But otherwise, you could also start at the bottom and then work your go to the parent, go to the parent, go to the parent until you hit you hit the root here, and then you're doing the code word in reverse here. So it's going to be 1 0 0, and so it'd be 1 0 0. You'd have to build it from the right to the left. Okay, there's our tree. There's our resulting encoding scheme. Right? Now, what is the code word length for each one of these? 3, 3, 2, 4, 3, 2, and 4. Clearly, it's going to be a variable length encoding scheme. And you can also verify, check out all of these. All of them are going to be prefix free. None of these are a prefix of any other, so you have a completely unambiguous encoding scheme here. What was the frequency? Right? No Kenneths are enrolled in this course. So I'm going to have to look it up myself. So 15%, 0.34, 0.05, 0.12. All right, if you don't get that joke, then I'll go ahead and play REM on Monday instead of today. It was Cornelius. All right. So there's our frequencies. What I want to know is, what is our average code word length? What's the average code word length? Now, to get that, all you have to do is say, well, 10% of the codes, the code words are going to be of length 3, 15% are of length 3, 34% are of only length 2, 5% are much longer with 4, and et cetera, et cetera. So you take the frequency, the sum of the frequency times the code word length. And that weighted frequency, that's the average, right? So in this case, it's going to be 0.10 times 3 plus 0.15 times 3 plus 0.34 times 2 plus ... And I won't beleaguer you with the basic mathematics here. It's just I'll just give it to you, 2.53. Okay? That's the average code word length. Is that better, right? Did we save anything? Did we compress anything? How did we compress? So the average code word length that we just computed was 2.53. Right? How big was our alphabet? How big was our character set? 1, 2, 3, 4, 5, 6, 7. So if we had a block encoding, right, then we would have had to have log of 7, log base 2 of 7. And we'll have to take the ceiling on that because you can't have a code word that is 3.5 bits long, right? So this is going to end up being 3, right? 8, what I was thinking ahead of here. If we had to encode this with ASCII, then of course it would be even worse. We'd have 8 bits per code word, right? So, but this is what we're going to want to focus on here. We compressed it from 3 bits down to 0.257. Or in other words, if we want a compression ratio, it's going to be the block encoding value minus the average code word length. In other words, how many bits on average did we save? and then divide that by the block encoding, and that gives us a 15.67% compression rate, or ratio. So if we had a 1 megabyte file, then we would only have a 850K file after compression with this particular example. Again, in practice, you can probably expect around 25 to 40% compression ratios for plain old English files. You'll see whether or not that holds up for the inputs that you're going to be programming or against. There are some degenerative cases. For example, if you just had random data has a lot of entropy. And so you can't compress it because everything is essentially it's a uniform distribution. Where if you've got say 10 characters that you're trying to encode, all of them are going to have equal length, in other 10% frequency. And so when you build this tree, it's going to end up being a full binary tree. And when that happens, everything is at the same level, right, or something like that. And so you're not going to have a very high compression rate for randomized data. And we do have examples like that in the grader for you. All right, good. So how might we program this? So some considerations here. First of all, you'd probably want to, there was a question before of, should we use a library to define tree nodes or just roll our own? In this particular case, I'd say I'd go with your own, so that you can have a little bit more control over it. Obviously, every node would have a parent if you want to travel up. Every parent, potentially a left and a right node. And of course, in each node, you want to keep metadata. You'd want to keep whether or not it's associated. It's an internal node with no association to any character. Its frequency, right, so that you can add them up. And at the very top, it should be 1. And of course, whether or not maybe if you want to, am I a left child of my parent or am I a right child of my parent, so that I can say that, well, I'm associated with 0 or 1, or you could do that on the fly. That's pretty easy. But what would the pseudocode look like? So again, the basic CS1 stuff, you'd have to go through and analyze the file and come up with all of the frequencies. But once you've got the frequencies, we'll assume that they're part of the input. The input is going to be an alphabet, a set of characters, right, with frequencies. And I'll just say that that's FREQ, right? And we'll output, not a Huffman code. What we're going to do is we're going to output a Huffman tree, right? And then you can build the code words from that tree, either again by doing a standard tree traversal, pre, in, or post order traversal starting at the root, or you can keep track of all the leaves and then just go from the root up to the parent for each one. Right? So what kind of data structure are we going to want? Remember let's see. Here we go. So again, smart data structures and dumb code are a lot better than the other way around. What I was doing here, visually, I was always selecting the least weighted one and then the second least weighted one, right? So that I could combine them into 2. And then I threw them back into consideration. Throwing them back into consideration was just on a piece of paper. So think really hard about what kind of data structure would allow you to efficiently grab the least, the minimum valued tree, the minimum weighted tree, and then the second minimum valued weighted tree, combine them, that's a separate operation, and then throw them back into the collection data structure efficiently. Pull the minimum out efficiently, and throw them back in for consideration. Hopefully you're thinking about a priority queue or a min heap. All right? And if we need another review of that, say from Computer Science 2, then I will go ahead. I can do that on Monday if you want. But otherwise, I would just use a min heap, right? That is going to order things by, or at least provide the minimum with respect to the weight of the tree. Okay. So for each character, I'm going to switch X. I'm going to create a single node tree, and I'm going to define the weight of that single node tree to be equal to the frequency of X. And then, sorry, insert T sub X into H. That's our heap. That's our min heap. So this is just the initialization phase. Clearly, this is going to be order n. Actually, this is going to run order n. This this for loop right here. Each insert is going to be order log n, and so in total, this is going to end up being order n log n. Okay, we're putting stuff into the heap data structure. That's just the initialization. Right? So pretty efficient. It's a quasi polynomial. Hopefully, the rest of our algorithm here is no worse than this over here. Okay. So while the size h dot size, if you want, is greater than 1. Right? Once it hits 1, then we can simply take the last. There's only one thing in the heap. That's our tree. That's our Huffman tree. We can take that out and return that. And that's what we'll do at the end over here. Okay. Otherwise, what we do is we pull out, we create a new tree node here. So this is a new tree. Right? And then we pull out the two minimum weighted trees from the heap. Again, weighted. The criteria there is going to be the weight of the tree. So once we've done that, I'll go ahead and do it like this. Give myself some more room. Right? So once we pulled those out, we will make T sub r dot left child be equal to T sub a, and T sub r dot right child. This is the consistency I was talking about, that it's not necessary. You could flip those if you want. You can randomize them if you want, but why? You're doing extra work for no benefit. So go ahead and just associate the minimum with the left and the larger one with the right. Okay. And then I need to define the weight of this new tree, TR. That's going to be the sum of the weights of the old tree, T sub A, plus the weight of T sub B. And then I need to throw this back into consideration. So insert T sub R into H. Right, there we go. So once that's all done, then I know that I've broken out of this while loop, which means that I only have one thing left in my heap, and then I will output H dot get min. The last one, just pull it out, and you can that's what you're returning. That's your final Huffman tree there. Right? So each one of these could be your elementary operation if you want, but the most expensive thing here, they're probably not creating a new tree node. That's just creating a new object. These are just references. This is just a plus right here. The real work is being done in the heap, right? This is going to be order log n. Right? Because if there are n things in the heap already, getting the minimum and then heapifying it, correcting it, fixing it, fixing up the heap, that's going to be require order log n operations. Likewise, this is going to be order log n. right, to get the next minimum. And then also putting it back in is going to be order log n. So we've got three heap operations. And how many times do we iterate over this? How many trees do we combine? Well, if we start with n trees and we stop when there's only one left, then that means that there are going to be n minus 1 iterations of the entire loop, right? And once we've got that, then, well, I mean, the 3 doesn't matter, right? Because we've already got order log n here. So this is going to end up being order n log n. If you use a priority queue or a heap, a min heap, in order to store stuff and put stuff in, take stuff out, right? And again, if we need a review of heaps, let me know, and we can do that on Monday. All right. So, time is it? We're good on time here. Good luck with programming that. At this point, we've covered everything that is relevant to Assignment 2. Assignment 2 is due on Tuesday next week, I believe. Go ahead and double check Canvas for to be sure. But otherwise, when we come back on Monday, if you want a quick review of heaps, what we're going to do is we're going to cover our last data structure, which is going to be hash tables. But as usual, again, the regular course of this the regular offering of this course in the summer, every Friday we traditionally have an open book, open note, open computer, closed partner test, not test but quiz. That's been cut for this offering. But I still want to cover them so that you get the benefit of what kind of quizzes or what kind of questions might appear on the midterm and the final, which again are going to be take home. So automatically open book, open note, open computer. But this is the quiz from last summer. And so to end the day here, we'll end it a little bit early as well because, of course, it is open. Well, I guess yesterday was technically opening day. But for me, it's opening day. Truncated 60-game MLB season. We'll call it the asterisk season because we don't know if it really counts or not. But anyway, so in celebration of that, we'll go ahead and do this quiz and then call it a day. Here's the first question. The first question was, the Toom-Cook algorithm was another algorithm similar to Karatsuba's multiplication algorithm that has a divide and conquer strategy for multiplying two many-digit numbers together. It's this particular variation of this algorithm, or a particular variation of the algorithm, splits the integer into three parts, each 1/3 the size of the original. The recursion, however, requires 5 recursive multiplications. Okay, so what we want to do is we want to set up basically a recurrence and then apply the master theorem to get an asymptotic characterization. And then we can say, is it worse or better than Karatsuba multiplication? So again, let m sub n be the number of multiplications made by this Toom-Cook algorithm. And we need to make 3 recursive calls on numbers that are 1/3 as big. Right? And just like Karatsuba multiplication, we end up doing no non-recursive multiplications. In the base case, we probably end up doing one multiplication with 2 one-digit numbers. But in the we probably end up doing additions and maybe other bit shifting operations non-recursively. But with respect to multiplications, we're not doing any. Right? So, by the master theorem, our coefficient here is 3. Our decrement here is, let me see. Oh, sorry, I misread it. 5 recursive multiplications. So, 5 and 5. There we go. 5 multiplications on numbers that are 1/3 the size. They split them up into thirds. And so B is still 3. And then our D, this is 0. This is f of n, which is going to be theta n to the d for what d? Well, in this case, d is going to be 0 because this is constant. This is just a 0. So the coefficient is, or the exponent here has to be 0. So 5 versus, remember, a versus b to the d for the master theorem. 5 versus 3 to the 0. Right? Hopefully you can come up with that 5 is greater than 1. Right? So by case 1 or 2 or 3, I forget which now, by case 1 of the master theorem, and this is why it's open book, open note, open computer. Let's see. It's also why whenever I write notes that I also put in an index and a glossary so that I can... Oh, no, I haven't compiled the index, darn it. All right, so I don't know where the... by the plug and chug, basically. If anybody knows, they can post on Piazza here. Okay, a quick... the only comment I see here is a quick review of heaps would be appreciated, and so we'll do that on Monday. By case 1 of the master theorem, or maybe it's case 3, I forget. I think it's going to be case... I think it's case 3, right? And that would give us n to the log base b of a, which is equal to n to the log base 3 of 5. And at that point, I'd have to pull out my calculator and ask Wolfram Alpha here, is it better than Karatsuba multiplication? And unfortunately, I don't even remember what Karatsuba multiplication was. So log base 3 of 5. Oops. 5. There we go. This is going to be order. Again, this is going to be irrational, so I'm going to make it a slightly bigger. 1.46, which I believe is a little bit better, 1.465, which is, I believe, is better than Karatsuba multiplication, but of course, I'd have to look at my notes on that. I don't memorize those things, and I don't expect other people to memorize those things. Okay. Part B. Consider the binary search tree in figure 1. For each node, indicate its balance factor. So this is what we covered yesterday with AVL trees. The balance factor of in an AVL tree was maintained to be 0, 1, or -1. And the balance factor was simply, remember, just the height of the left minus the height of the right. Okay? So I'm going to go ahead and move this over, and I'm not blocking it, good. So we can go ahead and redraw this tree over here, 25. I don't have a printer at home, otherwise I would have printed this out. 15, 9, and 5. There we go. And then 31. This is not an AVL tree, by the way. This is too unbalanced. This would have been rebalanced at some point of inserting all these things. But in fact, it is a binary search tree. And you can verify that just by looking at it, looking at each node and verifying that the left, everything in the left is less and everything in the right is greater. Right? So we'll go ahead and start at the bottom here of our balance factors, because the balance factor of any leaf is going to be 0. Balance factor on 50 is 0 minus 0, and again, it's not these zeros. The height of a single node tree is going to be 0. Right? The height of a single node tree is 0, so the difference is 0. And of course, that makes sense because this is a balanced subtree. Right? What about this over here? It's going to be 0 minus, and then the height of an empty tree by convention here is going to be -1, so -1, and we end up with +1. Okay. The balance factor here is going to be 1 in the height of the left subtree, and then -1 in the right subtree. So the difference here is going to end up being 2. Again, subtracting off a negative is going to make it positive. The height of the left subtree here is 2. The height of the right subtree, which is empty, is -1. So its difference is going to end up giving you 3. All right. Let's go back over here. 0 because that is a leaf. The height of the left subtree here is going to be 0. The height of the right subtree is 1, 2. So minus 2, giving you negative 2 over here. And we forgot 75 here. The height of the left subtree is going to be 1. The height of the right subtree is negative 1. So the difference is going to give you positive 2. It's skewed to the left. Positive is skewed to the left. Negative is skewed to the right. And you can see that in 75 and 31 here. What about this one? The height of this left subtree is going to be 1, 2, 3. The height of this right subtree is also 1, 2, 3. The length of the longest path from the root node, from any node down to a leaf. And so minus 3. The balance factor of the root in this case ends up being 0 because it is balanced, right? You've got a tree of this depth over here and a tree of the same depth over here. This has many more, not many more, but more nodes over here, fewer nodes over here, but that's not how you define balance factor, okay? All right, good. And then the last one is just kind of not memorization, but, go through insertion of each one of these into an initially empty AVL tree. So I'll go ahead and write those down: 30, 20, 10, 40, and 50. Then we'll come over here and we'll label all of the rotations that potentially happen and where they get inserted. So 30 gets inserted. Right? Balance factor, of course, there's 0. 20 will get inserted as the right child of 30. Balance factors, again, are going to be 0 for 20, and this one is going to be 0 minus negative 1, so it's going to end up being positive. It's skewed to the left, but 0, 1, and negative 1 are perfectly fine. So let's insert 10. That gets inserted as the left child of 20, and then we have a balance factor of 0, 1, 2, right? Because it's 1 minus negative 1, so it'll end up being 2 up here, and we need to rebalance. We look at the left child and see that it has a positive balance factor, so we know that it's skewed to the left, resulting in a right rotation. And we're left with 20, 30, and 10. There. 40 gets inserted as the right child of 30. 50 gets inserted, and let's quickly do the balance factors here. 0, negative 1 minus 0, so negative 1. 0 minus 1, so it's going to be negative 1. There's no rotations here, right? And that would, as you would expect, because if we do any rotations, that'll just merely push something else down over here, and it'll just be rebalanced to the left, but it's still balanced. So this is perfectly fine for an AVL tree here. But when we end up inserting 50, now what are the balance factors? 0, negative 1 minus 0, so negative 1. Negative 1 minus 1, so this is negative 2. Right? We need to rebalance here. Negative, we look at its right child, so it's skewed to the right. We look at its right child, it's also skewed to the right, so we need to do a rebalance here of a left rotation. And so 40 comes up to be the new right child of 20. And 30 goes down to be the left child of 40. 50 comes up here. If there had been a tree hanging off of this thing, where would it be? It would be less than 40, but greater than 30. So it would end up being swinging over here to be hanging off of this, right? And then you can say, well, where these two things are hanging off, they're still hanging off over here, T2 and T1, T2, 1 and T2. What if there had been an entire tree hanging off of this? It's less than 30, so it would end up being over here, right? But this is a simple enough solution for the quiz. Right. Same sequence of keys, but into an initially empty 2-3 tree. So 30, 20, 10, 40, and 50. 30, 20, 10, 40, and 50. Okay? So we insert 30. And that's a 2 node. It's a regular old node, binary search tree node. Then once we insert 20, then it becomes a 3 node. Right? It contains 2 keys and potentially 3 children, but no children in this case. Okay. Once we insert 10, then it temporarily looks like this, 10, 20, and 30. The keys become ordered, but this is over full. A 2-3 tree has 1 key or 2 keys per node, but not 3. So what we need to do is we need to take the middle element and promote it up, giving us 20, 10, and 30. There we go. A regular old binary search tree. 40 gets, you always insert into a leaf. So you come in, 40 is greater than 20, and this is a leaf, and it's not over a full, so there's an accommodation here, and we have 20, 30, and 40. We make that 2 node into a 3 node. There. 50 comes in, and 50 is it's added to this one initially, but now it's full, and so what we need to do is we need to promote the middle element up to the parent. So temporarily, what does that look like? 20 and 40 are now up here. 10 is still hanging off over here. But when we promote that up, we split that up into 30 and 50. Well, guess what? The parent is now a 2 node, or a 3 node, excuse me, with 2 keys, and so it needs 3 children, and we have 3 children to accommodate it. And that's it. Done. That's what it looks like in the end. You have room to add more stuff down here, but of course, the second that any one of these has now 3 keys, that gets promoted up, and it'll propagate upward and create and increase the depth of the tree. Okay. But I was keeping it simple for quizzes. Of course, there's nothing to stop you from using a tool either. All right. Have a good weekend. On Monday, I will go ahead and start with a review of heaps, and then we'll go to get into hash tables. I believe the midterm is on Tuesday or Wednesday. I forget. I'll have to look that up. But again, I'll have more details on that on Monday. But the way that it'll work is simply I will give the day. I'll still broadcast that day, live stream that day. But what I'll do is I'll take, like I've been doing with the quizzes, I'll take last year's midterm and we'll do it during the live stream lecture. Even before that, I will release the midterm probably in the morning sometime, or maybe the previous night, depending on when I get done with it. And you'll have all day, all the way till midnight to finish it. It'll be mostly written, I assume. So if you want to, you can use LaTeX. Otherwise, just go ahead and do that might be a little bit too much work to do the exam and to write it up in LaTeX. So we accept PDFs, we accept images, we accept clear screenshots from your phone. We've given you several app suggestions on how to do that, but it'll be OpenNote, OpenBook, OpenComputer, closed partner. The partner that you've been using for your assignments, you should not consult with them on the exam. It should be your own work exclusively. Okay? All right, I'll see you on Monday. Have a good weekend.